orbital period of the moon is the time period it takes for the moon to complete a full 360-degree orbit around the Earth. So, is that the same time period as it takes for the moon to complete the phase cycle? Well, let's see. Let's say we have the sun right here, and we have the Earth right here. I'm going to say the moon is right here. Actually, I'm going to make that slightly larger. Size doesn't really matter. That's just, I'm just going to call this the moon, even though the moon is slightly bigger than the Earth. That doesn't really matter. Now, at this point, the moon is in the new moon phase. So, if I were to represent this as the new moon phase, that would be the new moon phase. Now, when the moon is completing its orbital period, by the way, the orbital period of the moon is about 27.322 days, if you were just get an understanding of that. Basically, that would be the orbital period of the moon. Once the moon has completed its orbital period, that is a full 360-degree orbit around the Earth, during that time period, the Earth would have also been moving slightly around the sun. Let's say about to this position. The Earth will have moved slightly along its orbital path around the sun. And if the moon is doing a 360-degree orbit and it's returning to this position, then the moon will have to be in, well, this position. But here's the thing. This is not the new moon phase because the sun is over here as viewed from the moon. So really, there's something that looks something like this. And so that's about the waning crescent phase, right? This would be the waning crescent phase, approximately. And so as a result, the moon has not completed the phase cycle yet. There still has to be some extra amount of time that it needs to go through. I'm going to say P is the phase cycle of the moon. And it's going to be equal to the orbital period of the moon plus the extra time that the moon needs to basically go through in order to reach alignment with the Earth and the sun. I'm just going to draw these lines right here. This right here is the angular distance that the Earth traveled around the sun. And notice how, if I were to draw a line connecting the Earth and Moon here, these lines are parallel to each other. The reason why they're parallel is because the Earth and the Moon are basically the Moon has completed 360-degree orbit, and so as a result, these lines are parallel. So the angles here are the same, and this represents the angular distance that the Earth traveled during the Moon's orbital period. But here's the thing. Can we use this angle directly to figure out this time period little t? Can we just use this angle? Now, if the moon were to travel this angular distance to reach alignment with the Earth, Moon, and the Sun, then the Earth would have also continued to travel a little bit more along its orbital path. And as a result, the moon would have to travel a little bit more each time to complete its phase cycle. So this angle alone is not good enough. The problem that we're experiencing because of that is due to the fact that the Earth is still continuing to move around the sun. If the problem is the fact that the Earth is moving around the sun, then why don't we just treat it as if the Earth isn't moving? Now, if we're treating it as if the Earth isn't moving, then the Earth is still moving around the sun. It's just the Earth doesn't appear to be moving. The sun appears to be moving. And so if I were to draw that, I'm going to say I have the Earth right here, and I'm going to say I have the sun about right here. Let's see if you can still see that. That can still be seen. So this is the Earth, this is the sun. And I'm going to say the moon is initially in the new moon phase. Now, after the moon has completed its orbital period, the sun will move slightly along its orbital path, right? Because remember, it's the Earth that's really revolving. But as seen from Earth, if the Earth doesn't appear to move, then the sun would appear to be moving. The sun will appear to move approximately this much. So if I were to draw a line connecting the Earth and sun like this, notice how the moon would be there. And this would be the angular distance that the sun travels during the moon's orbital period. The moon will return back to this position, assuming the Earth doesn't move, right? Now, remember, if the moon moves this angular distance, the sun will have continued to move. But wait a minute. Wouldn't the angular speed of the sun just be the same as the angular speed of the Earth around the sun? In fact, that would be true. So let's just write that down. The angular speed of the Earth around the sun is the same as the angular speed of the sun around the Earth in this case. So, as a result, this is what we're going to use in order to understand how to find this extra time. We're going to use, or we are going to set the final angular positions of the Earth, or of the sun and the moon, equal to each other. Because the final angular positions will be when they're equal to each other. If the angular positions of the moon and the sun are equal to each other, then we know that they're in the same alignment with the Earth. It's slightly larger than this angle because this, I'm going to say, is the initial angular position of the sun. So the initial angular position of the sun. This is the initial angular position of the moon. Because the moon is initially right here, it needs to move a little bit of angular distance. So I'm going to say the initial angular position of the moon, I'm going to set that equal to 0. So that the initial angular position of the sun is just this angle right here. So, if I'm setting the angular positions of the moon and the sun equal to each other, I'm going to say the initial angular position of the moon plus the angular distance it travels to reach a final angular position, which would be the angular speed of the moon times that extra time period. And the reason why I know this is true is because basically because we know speed equals distance over time, so angular speed equals angular distance over time. If I were to say angular speed equals angular distance over time, therefore angular distance equals angular speed times time. That's where this is coming from. The angular distance that the moon is traveling to reach a final angular position. I'm going to set the final angular position of the moon equal to the final angular position of the sun, so that they will be in alignment with each other and the Earth. Equals the initial angular position of the sun plus the angular speed of the sun times the time period, this extra time period to get in alignment. And so what I'm going to do is I'm going to find a way to solve for this time. Okay, so we're setting the final angular positions of the moon and the sun equal to each other so we can find when they will be in alignment, when the moon and the sun will both be in alignment with the Earth. And that would conclude the end of the phase cycle. Okay, so we said that the initial angular position of the moon is 0, so I'm just going to say that's 0. So that's what matters. Okay, to make that 0. So what I'm going to do is I'm going to actually do it a little bit. This might look a little bit weird, but what I'm going to say is, so it can be a little bit less confusing to some people, is remember the angular speed of the sun around the Earth that it appears to move at is equal to the angular speed of the Earth around the sun. So that's just all I'm going to do. Now what I'm going to do is I'm going to try and actually solve for t. But the thing is though, maybe you don't know off the top of your head the angular speed of the moon around the Earth. Maybe you don't know off the top of your head the angular speed of the Earth around the sun. And so as a result, what I can do is I can just use angular speed equals angular distance over time to say, oh, well, after traveling an angular distance of 360 degrees, we have completed an orbital period of the moon. And this is basically the angular speed of the moon. Multiply that by t is equal to the angular the initial angular position of the sun. That's this angle right here. When the moon was completing its orbital period, the sun basically moved to its initial angular position that we're using. This is what it moved to. So, but the angular distance that it moved to is a fraction of what it ultimately moves to, right? Ultimately, the sun moves a full revolution around the Earth, or it appears to. But it's really, if we were to say what fraction of 360 degrees that is, well, really, it's the orbital period of the moon divided by the orbital period of the sun around the Earth. Orbital period of the sun around the Earth is equal to the orbital period of the Earth around the sun. So really, so orbital period of the moon divided by the orbital period of the Earth, right? Because this was really, this angular distance that the sun travels was during the time that a moon completed a full orbital period. And if we divide that by the orbital period of the sun around the Earth, which is the orbital period of the Earth, that's the fraction of the 360 degrees that we're using for this angular distance that the sun traveled. And then we add the angular speed of the Earth, which is just 360 degrees over the orbital period of the Earth times the extra time period. Now, what I can do is I can actually cancel out the 360 degrees on both sides. And the reason why is because if I were to divide 360 degrees on both sides, the 360 degrees would cancel out. And so what I'm left with is just some algebra. So T over Tm is equal to Tm over, or in this case, this is Tm plus T over Te. And so all I have to do now is just solve for T and then substitute it into here. So if I were to solve for T, I'm just going to cross multiply. So Te times T is equal to Tm times Tm plus T. So this is really Tm squared plus Tm T, right? Because it's just Tm times parentheses Tm plus T. Distributing that, you get this. So to solve for T, what I'm going to do is I'm going to just subtract Tm minus T on both sides. So I get T times Te minus Tm. So that's just from subtracting Tm T on both sides and then factoring out this little t is equal to Tm squared. And as a result, this extra time period is just Tm squared over Te minus Tm. So knowing this information, I could just say that the phase cycle of the moon is just equal to the orbital period of the moon plus the orbital period of the moon squared divided by the orbital period of the Earth minus the orbital period of the moon. So this is basically how we figure that out. And this works for any planet and any of its moons, basically. So what I'm going to do is I'm going to basically just use the calculator to just show you what this is. So what I'm going to do is I'm going to basically do the orbital period of the moon, which is 27.322. So if we do 27.322, and I were to add that, in this case I'm adding a fraction, so it's going to be the orbital period of the moon squared, which is 27.322 squared, and I were to divide that by the orbital period of the Earth minus the orbital period of the moon. Now the orbital period of the Earth around the sun is really just about 365.24, and then I subtract that by the orbital period of the moon, which is 27.322. And the answer I get, if you were to substitute these values in, you get 29.53 days about. In fact, it's really close to what you get on the internet. Basically, 29.53 days. That's the phase cycle of the moon. As you can see, it's slightly longer than the orbital period of the moon. And that's due to the fact that the Earth has to revolve a little bit more around the sun.